Hello and welcome once again to my YouTube channel on data analysis and research. Today we want to look at sample size estimation using power analysis. There are many formulas for calculating sample size depending on the study design. So there are sample size for case control, for cross-sectional, cohort study, experimental studies, and all that. But sometimes you may rely on a previous study or a pilot study to estimate the appropriate sample size for your research. So there are also different ways this can be done. It depends on the variable. So if you have a quantitative variable or continuous variable where you have mean and standard deviation, it can be used to estimate. You can also have a variable that is in proportions, like what we are seeing here. So today we want to look at a variable that is in proportion, so frequency and percentage. You can also use that to calculate the sample size. The same way you can use correlation coefficient. So the effect size, what we call the effect size, can be used to estimate sample size. So in that case, if you have more variable, maybe two or three, which are the main variables, you can estimate the sample size using all these variables and now pick the one with the higher sample size so that it will cover all sample size requirements for the work. So we are looking at a study. So this could be a previous study or a pilot study looking at this a case control. So determinants of retinopathy. So you have the cases, which is yes, those with the condition, and then no, the controls, those who don't have. So you can see the proportions here. So when it comes to hyperglycemia, those who don't have it, you see the proportion for the cases and the control. And then those who have, you've seen the cases and the control. And then using calculating the odds ratio, these are just the odds ratio, using the no as a reference. So you can see that there's a statistical difference. So those who have hyperglycemia have about 4.4 greater odds of developing retinopathy compared to the controls. The same way, if you look at glycemic control, good and poor, those who have poor glycemic control have about 3.5 greater odds or likelihood, 3.5, 2.5 times likelihood of developing retinopathy. So based on this, if this is a previous study or a pilot study, we can use this to estimate. If we are doing a similar study, which also involve these uh, variables, we can estimate the minimum sample size required for this study. So this can be done in SPSS version 27. So 27 and better versions, they have this. So it's called power analysis. So if you come to SPSS, you go to analyze. So the first you see power analysis. So you can see you can use mean. So means one sample t-test paired independent and over. So depending on the analysis you intend to do, you can use any of these to estimate. If you come to proportions, you can see one sample binomial, related sample, then independent. So in this our case, we are using case control. So we are going with the independent sample binomial. So that's what we saw. Correlation, Pearson, Spearman, partial, regression, univariate. So there are a lot of options when it comes to power analysis. But we are looking at proportions. So go to proportions. We are looking at independent sample. So this is case control. The samples, the cases and controls are independent of each other. So we type in this, we select this. But there are other options you need to select. You should know the power. So the power you want, the confidence interval, your alpha value or margin of error. So this should be determined. Then you now input the proportions to determine your minimum sample size. So if you look at this, uh, normally, usually for power, the minimum normally is 0.8. So you can use 0.8. And then case control, you also look at the ratio. Are you doing 1 to 1, 1 to 2, 1 to 3, 1 to 4? Usually 1 to 4 is the highest you can go. So 1 to 4, so that means your ratio of cases to control is 1 to 4. So either we will leave this one as 1 to 1, so that means you have equal number of cases and controls. So we can leave it. So we are estimating sample size. We are not estimating power, so we will not select this. We are estimating sample size. So we now come to proportion parameters for a group. So now we are going to input the proportions. So we go back to our previous study or pilot study. So let's look at hyperglycemia. So we'll use a yes because that is where the significance lies. So you see that our proportion is 65.5 here, and this is 26.3. So 62.5 to 6.3. So let's see, 62.5 to 6.3. Okay. All right. So let me cross check again. So 62.5 and 26.3. So 5.5 to 6.3. So let's okay. So if you convert this to percentage, so you need to use them as by dividing by 100. So that will be 0.625 and 0.263. Okay. So 0.625 and 0.263. Okay, so these are our proportions for group 1 and then group 2. So our alpha value significance is 0.05. Okay, so I think we are set. So it means if this 0.05, your confidence interval is 95 or 0.95. So that is fine. Okay, so test method, so chi-square, can leave it normal approximation for the method. So non-directional, so two-sided. We want two-tail analysis. So one two-tail, so two-sided. So that is what we want to do. So I think everything is okay now. We can go ahead. So select OK. So this is our results. So after the calculation, so you can see for group 1, the minimum sample size you need is 29. For group 2, it's also 29 because we are doing 1 to 1. So your total sample size will be 29 plus 29. Okay, so that will be like 58 or so. So you see the power being adjusted is 0.809. So 0.8. Alright, so the odds ratio derived from it is 4.6. So this is what we saw as the odds ratio in our previous study. You can see the significance level is there. So this is how you can use proportions from a previous or pilot study to estimate the minimum sample size. So let's look at this again. Let's see if we change the proportions, the ratio, what will happen. So if you don't want 1 to 1, and let's put 1 to 4. So the highest, so 1 case to 4 controls. So we still maintain all the other parameters. And then let's see what we get. So you can see, so because it's 1 to 4, so the first group cases are 17, the controls are 68. So the power is 0.805. Okay, so automatically when you change the proportions, it will adjust to also give you the minimum sample size per age group. So what about the power? The power will affect the the sample size you need. So let's make this 0.9 and still leave the ratio of 1 to 4 and see what happens to the sample size. So if you increase our power to 90%, you can see that the minimum sample size for the cases have increased from 17 to 23, and for the controls have increased from 68 to 90. So you see our power 0.9. Okay, so as you alter the parameters, your value, so depending on your study, you have to determine even your alpha value. Depending on the type of study, you can make it 0.01 or 0.001. So example, let's leave all parameters here the same and then change our alpha value and see what happens. So instead of 0.05, we want a very high significance, we make it 0.001. So let's see what happens. So whether there will be changes. Okay, so we have changed that. Let's compare with the previous one. So you see, as you increase power or try to make the alpha value smaller, so you see that your sample size will continue to increase. So from 23, it's now 45, and from 90, it's now 179. So the the power and the other values are still the same, but we have changed the significant level, the alpha value. So you can always go back depending on your study. So your study design will tell the power you want, the alpha value you want. Then based on the previous study of a pilot study, you can get your minimum sample size. So if we are considering other, so if uh, this is your primary variable or aim, your primary aim is hyperglycemia, but this is a secondary uh, aim at least. But you can also use that to calculate to see the minimum sample size. So you now pick the higher value from there. So this is, so we enter this 0.6 and 0.388 and see. So let's do for the glycemic control. So we'll still maintain. So let's see. So let's assume that we want to maintain the recent parameters. We want to maintain all this, but we are not changing these parameters, so the proportions for glycemic control. So 0.6, 0, and then 0.388. Okay, so for the glycemic control, so this is what we have. So you can see for the hyperglycemia is 45 here, glycemic control is 142, and then for the controls it's 179, and we have 567. So you can see that one is quite larger. It's larger than the first one. So the higher the difference, so the difference, so you see that the more the difference or the larger the difference between the groups, the smaller the sample size. The odds ratio here is 4.37 and here is 2.499. So the higher the difference, the smaller the sample size. So if these were not significant, you see that even the sample size will be larger. So usually, if it will be good for you if your previous study or pilot study finds a significant difference between your cases and controls. So that normally brings the sample size to a manageable level. Alright, so thank you very much. This is how you estimate sample size using power analysis for proportion. So a variable that has in proportion, so like odds ratio, so you can use that. You can also do for mean, standard deviation, you can do for correlation, you can do for uh, so depending on what, so whether independent or two-sided, one tail, all can be analyzed depending on your study design. design or protocol. So thank you and see you once again. But before you go, please like my channel, subscribe, and also share this to your colleagues who are interested in data analysis and research. So bye for now and see you later.